Hi, welcome to Algebra 2 Common Core. Today in lesson number 5, we're going to learn how to calculate conditional probabilities. So let's start with the definition of a conditional probability stated in the box in your notes. In words, this means the probability of an event A occurring given that another event B has already occurred. In symbols, we're going to write it as P, probability, of A given B. You'll notice that A given B is going to be written this way with an A, then a vertical line, and B, and we would read that as the probability of A given B. Now our formula for that is going to be, let's find the probability of both events occurring, so the probability of A and B, and then let's divide it by the probability of just B occurring. So again, we're saying that B has already occurred, and then what's the probability of both of them occurring in the numerator? Now, likewise, I could have said, what's the probability of B given A? And that's going to be written as the probability of A and B, or B and A, those are interchangeable, divided by the probability of A. So it depends what my given is and what probability I'm trying to find for the order in which I write this. Let's look at the example inside the box. In a school of 1,200 students, 250 students are seniors. So I'm going to mark that down. Seniors, 250. 150 students take math, so I'm going to call that M. 150 students take math. And 40 students are seniors who are also taking math. So S and M is going to equal 40. Now, I've been given this information as numbers, but of course I could write probabilities. Now the question is asking, what is the probability that a randomly chosen student is taking math given that they are a senior? So the way that we're going to write that is, what is the probability of a student taking math given that they are a senior? So our formula is going to be, let's first of all figure out the probability of both things occurring at the same time. So the probability of a student taking math and being a senior, and we're going to divide it by the probability that they are a senior. Now again, let's go back to our original statement. We know that the school has 1,200 students. So the probability of a student taking math and being a senior is going to be those 40 students that we know are taking both, are a senior and are taking math, out of the 1,200 students. So we're going to say that that probability is 40 over 1,200. The probability of them being a senior, remember that there are 250 seniors. So out of the whole school, 250 are seniors out of 1,200 students altogether. Now we can easily see that when we're dividing fractions, we're going to do our keep change flip. So 40 over 1,200 times, so change to multiply, the reciprocal of the denominator, 1,200 over 250. This is so convenient for us because we see that the 1,200s are going to cancel. So I'm getting an answer of 40 over 250. And yes, I could reduce that by 10 and say that that's going to be 4 out of 25. Now, of course, I could also put that in my calculator and get the decimal. That decimal is going to be 4 out of 25, which would be 16 out of 100, which would be 0.16. So I can either leave my probability as a fraction or as a decimal. Now in example number 1 written below, we're given our information in a two-way table. So you'll notice all the information in this table. It says a survey was taken to examine the relationship between hair color and eye color. The chart shows the proportion of the people surveyed who fell into each category. If a person was picked at random, find each of the following conditional probabilities. So then a conditional probability means find the probability of something happened given that something else has already occurred. So let's look first of all at our table so that we're sure that we understand it. Along the top we see the three options for hair color: black, blonde, and red. Along the side we see the three options for eye color: blue, brown, and green. We see that the decimals inside here are going to already be proportions. So when I look at my total here, I see that the total is equal to 1 because all of the proportions, no matter which way I add it up in the table, is giving me a total of 1. So in part A it says, find the probability that the person picked has brown eyes given that they have blonde hair. So the way that we would write this notation, the probability of brown eyes given blonde hair. So for our formula, we're going to say, let's first of all figure out the probability that a person has brown eyes, but also has blonde hair. And we're going to divide that by our probability of the given, so probability of having blonde hair. Now, when our information is given to us as a decimal, we're just going to read off those decimals. We don't even have to calculate proportions because they're already in proportions for us. So the probability of brown eyes and blonde hair, if I follow across the brown eyes row and follow down the blonde hair column, I see that that probability is equal to 0.10. So that's going to be my numerator number, nice and easy. Now, the probability of having blonde hair, I need to look at everybody in the whole group that has blonde hair. So that's going to be this column right here. So all of the people that have blonde hair would be a proportion of 0.35. So I'm going to say let's take that 0.10 and let's divide by 0.35 because that's the proportion of people that have blonde hair. Now in this situation I would go to my graphing calculator and I would divide that and I would get my final answer of 0.29. Let's look at part B where it says find the probability the person had red hair given that they had green eyes. So the probability I'm trying to calculate is the probability of red hair given that the person has green eyes. So I need to know the probability of having red hair and also green eyes. So I always want to do the and in the numerator. But then we're going to divide by the probability of having green eyes because we're specifically saying what happens if I know the person that I've selected already has green eyes. So looking in my table, I'm going to say the red hair would be this column right here. The green eyes would be this row right here. So red hair and green eyes would have to be a 0.15 in my numerator, divided by the probability of having green eyes. So look at my green row and say, oh, the total of all the green would be 0.25. So let's divide by 0.25 because that's the probability of having green eyes in the whole group. Doing that division, I see that it turns out to be 0.60. And again, I could have written these as fractions, but because I was given the information as a decimal, it was just as easy to divide on my calculator. In example number 2, we're looking at a survey. We surveyed members of our school club about the type of end-of-the-year party that they would like. And here we have shown the two-way table showing the results. Notice that this two-way table is not completely filled in. So when that happens, we're going to have to complete our table so that we can then use the information in the table to find the conditional probabilities. So for miniature golf, if I have 8 males and 4 females, that's a total of 12 students. For skating, 3 males and 10 females give me a total of 13 people. 9 males want laser tag, 6 females want laser tag, so altogether there are 15 people that want laser tag. Add to get my total number of students, so 12 plus 13 plus 15 is giving me a total of 40 students. Now go the other direction. 8 plus 3 plus 9 is giving me 20 males that were surveyed. 4 plus 10 plus 6 is telling me that there were 20 females surveyed. So always fill out your table so that you can then use that information. So we want to find the conditional probability of those wanting laser tag given that they are female. So that's going to be the probability of laser tag given female. So we know, of course, that we're going to have to take the probability of laser tag and female divided by the probability of being female. So to do that, the laser tag and female group is going to be this group right here. How many are there all together? 40. So we're going to say that's 6 out of 40. I didn't leave much room on this one. Divided by the probability of being female. Well, if I look at my entire female population, that's 20 out of 40. So I'm going to say 6 out of 40 divided by 20 out of 40. Do you see that when we do the keep, change, flip, the 40s are going to cancel? So I see that I'm getting 6 out of 20, or as a decimal, that's going to be 0.3 because it's 3 out of 10. So my answer for that probability, 0.3, kind of squished in there. I think I'm going to go below to do part B here. So for part B, it says find the probability of those wanting mini golf. So the probability of mini golf given that they are male. So that's just going to be the probability of mini golf and male divided by the probability of being male. So to do this calculation, the probability of mini golf is going to be, we're looking at mini golf and male. So mini golf and male is this group right here, so 8 out of our 40 students, divided by the probability of being male. Well, there were 20 males surveyed, so half of them are male. So that's going to give me 8 out of 20, and 8 out of 20 as a decimal gives me 0.4. So 0.4 for that calculation. Okay, do me a favor and try part C, and then come back and check your work with mine. Welcome back. Check your work with mine. So you'll notice that I did the probability of being female given that the student wanted skating. So we want the probability of female and skating in the numerator. So female and skating is 10 students out of 40, divided by the probability of wanting skating. So the students that wanted skating, 13 out of 40, so that goes right here. So therefore, the 40s end up canceling, and I get 10 out of 13, which is 0.77. Now, if you think about that, that makes sense according to our table. It says, what's the probability that you are female given that you wanted skating? Well, if you look at your table, you see that most of the people that wanted skating are female. So it makes the most sense to say, oh yeah, this number of students out of this many who wanted skating are female. So the 10 out of 13 also comes from that line there. So right there, probability of skating, given that I'm only looking at the females. So 10 out of 13 or 0.77. Now for this one, I spread my work out a little bit more. Example number 3 says Melanie is on the dance cleanup committee. She collects empty Dr. Pepper and Sprite cans from the tables. She knows there were 4 12-packs of Dr. Pepper and 2 12-packs of Sprite at the start of the dance. She finds 30 cans on the table, of which 16 were Dr. Pepper. She realizes that some were thrown into the recycle bin already. So first of all, we're going to start by completing the two-way table for the data and then be able to answer the conditional probability questions. So the first thing that we know is that altogether there were 4 12-packs of Dr. Pepper. So to begin with, we had of Dr. Pepper 4 times 12 or 48 cans. There were two 12-packs of Sprite, so 2 times 12 gives me 24. So altogether we had 72 cans of soda. She finds 30 cans on the table, so I'm going to put that in the total for the table. 16 of those were Dr. Pepper. So of course we can subtract and say, well, the other 14 must have been Sprite. So now let's take a look at the recycle bin. The Dr. Peppers, there had to be 32 put in the recycle bin. The Sprites, there had to be 10 put in the recycle bin, so that we had 42 put in the recycle bin altogether. And again, if you look at all your columns and all your rows, they have to add up correctly. So now if we want the probability of Dr. Pepper, given the fact that the can was left on the table, we're going to say that this is the probability of Dr. Pepper and left on table divided by the probability of those that were on the table. So looking at my chart, I see that Dr. Pepper and table would make this number right here, 16, out of the 72 cans altogether. So 16 out of 72 in the numerator, divided by the probability of the cans left on the table. So if I look at all the cans that were left on the table, there were 30 left on the table. So that's going to be 30 out of 72. So when I do that division, I get 16 out of 30, or that reduces to 8 out of 15. I'm going to leave this one as a fraction, just for fun. Now, when I look at this, I can also say, let's just take a look at the row that was the cans left on the table. Out of those, which one were Dr. Pepper? 16. So 16 out of 30 also gives us that answer. Let's go ahead and do part B. We've got the probability of the can being in the recycle bin, given that it's Sprite. So we want the probability of recycle bin given Sprite. That's just going to be the probability of recycle bin and Sprite divided by the probability of Sprite. So for this one, recycle bin and Sprite gives us 10 cans out of 72. Divided by the probability of Sprite, there were 24 cans out of 72 that were Sprite. So canceling off the 72s, I get 16 over 24. And in this case, I'm ending up with 2/3 of the cans. I'm sorry, I couldn't read my writing there. That's actually not 2/3. Uh-oh, can't erase that. I'm just going to cross that answer off. That should be 10 out of 24. So 10 out of 24 reduces to 5/12. I didn't have the right answer on that one. Sorry about that. Continuing on to part C, I've got the probability of Sprite given the fact that the can was in the recycle bin. So I want the probability of Sprite and recycle bin divided by the probability of recycle bin. So looking at my table, Sprite and recycle bin, that's going to be 10 out of 72. Divided by recycle bin, 42 out of 72. So that reduces to 10 out of 42, which is 5 out of 21. And finish up part D, probability of the can being left on the table, given that it was Dr. Pepper. So we want the ones that were left on table and Dr. Pepper. So that's this one right here, 16 out of 72. Divided by the probability of Dr. Pepper. Probability of Dr. Pepper is 48 out of 72. And when we cancel off those 72s, we get 16 out of 48, which reduces to 1 out of 3. Now what I'd like you to do with example number 4 is complete our total rows and columns for example 4 about how did students get to school today, and then we'll come back and take a look at those conditional probabilities. So go ahead and check your answers with mine. I think at this point we might be able to shorten up the process a little bit. We've been able to use the formula all along, which will always work, but we can also just look at parts of our table to determine these probabilities. So for example, if I want to find the conditional probability of selecting those who walk to school given that they are juniors, what I'm really doing is just looking at the row of the juniors right here. So if I know that I have a junior, that means that I am specifically talking about out of 109 students that are juniors. Which of those students walked to school? So out of the juniors, the ones that walked to school were 4 of them. So I would put in the bottom the number of students that are juniors, and in the top the juniors that walked to school. Now again, would I get the same exact answer if I did the probability of walk and junior divided by the probability of junior? I would get exactly the same answer. So if we want the probability of a sophomore, given that they rode the bus, I want to start by looking at the group of students who rode the bus. So the students that rode the bus are going to be this group of students right here. So my bottom number is going to be that 221. So I want out of the ones that rode the bus. Which ones are sophomores that rode the bus? There were 76 sophomores that rode the bus. For part C, find the probability of a junior given the fact that they walked to school. So I want to start with the group of students that walked to school because I have given that they have walked to school. So the students that have walked to school, there were 13 of them. How many of them were juniors? 4 of them were juniors. And again, I get exactly the same answer if I said the probability of junior and walk divided by the probability of walking. For the last one, the probability of those who rode the bus to school, given that they are a sophomore. So I want to start with the group that are sophomores. So there were 123 sophomores. So that number goes on the bottom because I know that to be true. Now I want the bus riders out of that group. 76 of them out of that group rode the bus. So 76 out of 123. Please read example number 5 and do it on your own, and then come back and check your work with mine. For example number 5, we're going to have to rely on our formula because we don't have a two-way table to look at rows and columns on. So first of all, I know that the probability of a student buying a lunch is 0.60. The probability of a student buying a lunch and a dessert is 0.10. The question says, what's the probability that a student who buys lunch also buys dessert? So the question really is, what's the probability that a student buys dessert given the fact that they have already purchased lunch? So our formula is written on my note packet here. So I'm going to say 0.10 divided by 0.60, and that reduces to 1 out of 6. Thanks very much for working today with conditional probabilities. And have a good night, and we'll see you next time. Bye-bye.